Welcome to my talk on hardware-backed authentication patterns. My name is Victor Liboslavsky. I've been in tech for over 25 years, and I'm currently a principal software engineer at Fleet Device Management. I'm also the tech lead for our security and compliance product team. At Fleet, we make endpoint telemetry for corporate security teams and device management for corporate IT teams. Let me start with something we're actually really good at. We're exceptionally good at proving the server's identity. Really good. Today, when your browser connects to a website, there's a whole stack of machinery that kicks in automatically. TLS everywhere, certificates issued and rotated, certificate transparency logs, root CA certs, public key pinning. We've made it genuinely hard to impersonate a server. 20 years ago, HTTPS was optional. Today, browsers refuse insecure connections by default. We effectively solved server identity. But here's the part that surprised me once I really stepped back and looked at it. We spent 20 years proving who the server is, and almost no time at all proving who the client is. The server knows exactly who it is. It has a certificate, a chain of trust, transparency logs. But when a request comes in, the server mostly sees a header, a token, a string, and that's it. If that string looks right, the server shrugs and says, "Sure, you must be my client." Let's think about that for a second. The server knows exactly who it is, but it has almost no idea who is calling it. In a lot of systems, what we really mean by client identity is the request is coming from somewhere or someone who has that key. Not a specific device, not a specific piece of software, not a specific workload, just whoever has the string. So when the request comes in, the server can't reliably answer basic questions. Is it coming from your real application, a copied binary, a compromised device, or a replay from somewhere else on the internet? Most of the time, the server can't tell. The attackers know this. They don't go after the part of the system that's hardened by cryptography audits and transparency logs. They go after the part we never really hardened. So what does that blind spot look like in the real world? It usually doesn't look dramatic. There's no 0-day, no buffer overflow, no nation-state actor. In most incidents, nobody breaks anything. Instead, someone gets hold of a credential that already works. Maybe it's an API token copied off disk, maybe it's a certificate extracted from a container image, maybe it's a signed request captured and replayed. However it happens, the effect is the same. The attacker doesn't need to be clever. They don't attack the server, they don't attack TLS, they don't attack cryptography. They just start using the system the way it was designed to be used. And from the system's perspective, everything looks legitimate. The math checks out, and that's the problem. Because the attack wasn't an intrusion, it was impersonation. The attacker didn't force their way in, they showed up with something the system already trusted. And once they do that, the system can't tell the difference anymore. That's the uncomfortable part. Not that attackers are breaking our defenses, but that they don't need to. So the real question becomes, what does it actually mean to prove you're a client? Not just that you have something the system accepts. So let's make this concrete. Imagine we're building a security agent running on corporate laptops. It needs to call home to our backend. The backend needs to know, is this a real agent on a real device in a healthy state? Next, let's briefly talk about what we actually mean when we say the client authenticated. In most systems, the most common security use case is to have an API key. An API key is just a string the server recognizes. If the string matches, the request is accepted. There's no claim about who generated the request. API keys are basically shared passwords. The rule is just, if the string looks correct, the request is trusted. The same rule shows up again with bearer tokens. OAuth access tokens, authorization headers, session tokens. Different formats, same idea. The token isn't tied to who you are. It isn't tied to where you're running. It isn't tied to what produced the request. It just says someone who has this string made this call. What about JWT, JSON Web Tokens? They're everywhere. JWTs became the de facto identity token format in OAuth 2.0, where they're sent in the authorization header. That pattern is now universal for many API tokens, even if you don't use OAuth explicitly. A JWT signs its own claims, but it does not bind those claims to the HTTP request itself. If someone obtains a valid token, they can replay it. It's cryptographically stronger than an API key, but operationally it's the same model. Possession equals access. So in the previous examples, we were essentially dealing with tokens. When we say the client proved who they are, what we usually mean is they proved they possess the right bytes. That's not identity. That possession is perfectly copyable, and if identity fits on a clipboard, it is not identity. At this point, some of you may be asking, what about asymmetric cryptography? We use strong cryptography, public key cryptography, signatures, certificates, mTLS. This stuff feels standard and solid. So this picture shows the standard mTLS handshake. mTLS is the gold standard for authentication, where both the client and the server present certificates during the TLS handshake. It's built into the protocol, fast and well supported across operating systems and browsers. In practice, though, those keys usually live on disk in configuration files mounted in the containers, or in the best case, loaded into process memory. And once a private key exists in those places, mTLS has no way to tell whether that key was copied, whether it's being used somewhere else, whether it's the original client or a clone. From the server's perspective, every successful handshake looks identical. The certificate is valid, the signature checks out, the connection is authenticated. mTLS proves the key was used, it does not prove where that key lives. So back to our agent. If its private key lives in a file and that file gets copied to another machine, the backend cannot tell the difference. The handshake succeeds either way. And also in most real system architectures, mTLS is hard to use and even harder to reason about. TLS is often terminated at a load balancer. Certificate verification happens upstream from the application server. Identity may or may not be forwarded downstream as metadata. So the application server ends up trusting that someone somewhere already verified this client. Now, mTLS is doing exactly what it's designed to do. It's just answering a more specific question than we often assume. So again, the problem isn't cryptography, it's key custody. But also, some of you may be thinking, what about workload identity? That's not using static tokens. And yes, you're right, it's a great progress for security. If you're running Kubernetes, if you're on a major cloud provider, if you looked at SPIF, a secure production identity framework for everyone, or similar models, the basic idea is this. Instead of a client showing up with a long-lived secret, the platform steps in. The platform says, this workload is running here. It was scheduled by me. It's running on this namespace on this node with this identity. Based on that context, an identity is issued, often automatically, often just in time, often with very short lifetimes. Keys are rotated frequently, credentials expire quickly, and all of that is a real improvement. We have moved away from hard-coded strings. We've moved away from secrets that live forever. Identity is no longer just what you present, it's also where you are. However, all of this still lives inside the platform. The platform is asserting identity on behalf of the workload. The workload itself isn't proving anything intrinsic. So if the node is compromised, if the runtime is compromised, if the control plane is compromised, then everything running there inherits that compromise. From the application server's point of view, the identity still looks valid, the credentials are still fresh, the context still checks out. But if I can clone the node, I can clone the workload, and I can clone the identities. For our agent that we're building, that means if someone snapshots the VM or clones the environment, the identity comes with it. The context is different, but the cryptographic identity is identical. So workload identity absolutely moves us forward, but it doesn't give us a physical anchor. It gives us context, not uniqueness. It gives us assertions, not immutability. And that's the key limitation. We moved identity from strings to context, but context is still not anchored. So up to this point, we've talked a lot about identity, tokens, keys, certificates, context, workloads. So before we go any further, we need to slow down and ask a more basic question. What do we actually mean when we say hardware-backed? Because that phrase gets used a lot, and depending on who you ask, it can mean different things. When most people hear hardware-backed, they picture something like this. A private key exists, it's generated securely, it's stored somewhere safe. Maybe encrypted on disk, maybe loaded carefully into memory. That sounds good. That sounds secure. But that's not the property we're actually interested in. The real shift with hardware-backed identity isn't where the key is stored, it's what the system allows you to do with that key. Here's the defining property. With hardware-backed keys, you can use the key, but you cannot read it. Not should not, but cannot. There's no API to export it. There's no syscall to dump it. There's no clever trick or workaround to print it out. The key material literally never leaves the hardware boundary. That single constraint changes everything. So in software system, identity is copyable because keys are copyable. In hardware-backed system, identity becomes non-replicable because the key never exists as exportable data. That's the shift. Now, back to our agent. Even if someone copies the disk, the container image, or the binary, they cannot copy the private key. The backend would only accept signatures from the original device. Instead of treating the key as data, hardware treats it as a capability. You don't get the key, you get an operation. You can ask, sign this payload, decrypt this blob, respond to this challenge. The hardware performs the operation and returns the result, but the key itself never crosses the boundary. This is where some important vocabulary comes in, and we're going to be using these words very precisely for the rest of the talk. First, root of trust. A root of trust is the thing the entire system ultimately relies on. It's the part you assume is correct when everything else might be compromised. In hardware-backed identity, the root of trust is the hardware itself, not the operating system, not the container runtime, not the workload, the silicon. Second, non-exportable key. As mentioned earlier, this doesn't just mean we promise not to export it. It means hardware will not serialize it, the hardware will not reveal it, the hardware will only apply it internally. If the attacker steals your disk, they don't get the key. If they dump your memory, they don't get the key. If they copy the container image, they don't get the key. They can copy everything except the thing that matters. Third, sealed and unsealed. Hardware doesn't just hold the key, it controls when they're usable. A key can be sealed, meaning it exists, but it cannot be used yet until specific policy conditions are satisfied. Usage is gated by hardware, not by application logic. Which brings us to the next term, measurement. Measurement is how hardware answers the question, what is the system actually running right now? It takes cryptographic hashes of firmware, bootloaders, kernels, sometimes even configuration, and those measurements become part of the hardware's internal state, and keys can be bound to those measurements. So the hardware can say, I will only use this key if the system looks like this. If the system changes, the key stays sealed. And once identity becomes non-replicable and bound to measured state, the next question becomes obvious. How does a remote system verify that? That's where attestation enters. So hardware-backed identity isn't about stronger cryptography. It's about introducing a property we didn't have before, non-replicability. Attestation is what makes that property externally verifiable. For our agent, this is how the application backend learns that the key was generated inside real hardware and is bound to a measured boot state and not simply that a signature verified. So when you hear the term hardware-backed authentication, don't think where the key is stored, think who can use this key, under what conditions, and can that capability be copied? Because now possession isn't just logical anymore, it's physical, and that's the turning point for everything that comes next. So now that we've grounded what hardware-backed actually means, let's zoom in on some concrete implementations, starting with a real piece of hardware that's been shipping at massive scale for years, the Trusted Platform Module, or TPM. You've almost certainly run on machines with one. It's an international standard that's over 1,000 pages long. So, of course, we'll try to cover it in under 10 minutes. But on a serious note, this is complex stuff, and this is where a lot of teams get lost. We're talking about a secure crypto processor that gives you three things in one place: device identity, key protection, and platform integrity. And it can be its own chip, it can be implemented as firmware, or integrated into an SoC, system on chip. But in all cases, it exposes the same security model. The important shift is that a TPM is not just storage, it's a policy engine for cryptographic operations. Inside the TPM, everything starts with seeds. A TPM has multiple authorization hierarchies, each rooted in a different internal seed provisioned by TPM, by the TPM implementation, and never readable or exportable. You can never read these seeds, you can't export them. They're internal secrets that anchor all derived keys. Practically, that means you can create keys that are permanently bound to one TPM without you having to manage a master key in your own code. The TPM is the only thing that can derive and apply those roots correctly. TPM keys live in separate hierarchies for different purposes. Endorsement for attestation, owner for application keys, and platform for firmware trust. The important idea is separation. There isn't one global God key. Different roots enforce different policies at different uses. Now, two keys matter a lot for how people reason about TPM identity: the endorsement key and the attestation key. And this is where I want to pause, because this is also where a lot of teams, including some of our customers, have had real confusion and real frustration. People hear TPM identity and assume there must be one key that represents the device. That assumption turns out to be wrong, and it causes some problems. The endorsement key, or EK, is rooted in the endorsement hierarchy. It's derived from the TPM's endorsement seed and represents the TPM's manufacturing identity. Conceptually, the EK anchors statements like, "This is a genuine TPM of a known type produced by a known manufacturer, and this key was generated inside that specific TPM." You generally don't use the EK for day-to-day signing. Its job is to bootstrap trust in the TPM itself. I want to repeat that. EK is just for bootstrapping trust and cannot be permanently relied upon. That's because in the real world, firmware updates and TPM clears can regenerate it. That mismatch is where many systems tend to break. The attestation key, or AK, is created by the TPM also under the endorsement hierarchy. The TPM certifies the AK, most often using the EK, so AK can sign evidence on behalf of the TPM. This is the key that says, "These are my measurements. This key was generated inside this TPM. These conditions were enforced." The EK establishes trust. The AK speaks with that trust. But the AK is not a device identity. It's an evidence key, and it's meant to be rotated. If your system breaks when an AK changes, it's usually because evidence was treated as identity. Then you have your actual application keys, signing keys, decryption keys, storage keys. These live under the owner hierarchy. These are the ones you use for client and device identity, for request signing, for decrypting a local secret, whatever your workload needs. In TPM terms, they're objects with attributes. Depending on the attributes, some keys can sign, some can decrypt, some are restricted to specific operations, and some are constrained by policy. The TPM is the one that enforces the rules of use, not your code. Here's the hierarchy model you can keep in your head: seed to parent to child key. Parent keys are used to wrap child keys. Child keys are stored as blobs that are all only usable when loaded under the correct parent. This is how TPMs scale despite limited non-volatile storage. You don't need the TPM to persist every key forever in silicon. Many TPMs have limited memory, and as an application developer, you can't rely on the TPM of your client to have space for your identity key. You persist these wrapped key blobs externally on disk, and the TPM unwraps them only under the right parent and policy. The reason this works is because parent keys are reproducible. If your application creates a primary key under the same hierarchy with the same template and the same authorization, the TPM will deterministically derive the same key again. That means you can treat parent keys as reconstructible anchors rather than assets you must store like files. It's a practical trick, less state to persist, but still bound to that TPM's internal seed. Now we get to the most important integrity concept, PCRs, Platform Configuration Registers. PCRs hold measurements of the boot process. They're not logs, they're not configuration flags, they're registers that accumulate cryptographic hashes. Accumulate is important, they're extended, not overridden. And here's a key nuance. PCRs aren't writable by normal software. They're updated through controlled measurement flows. The point is that they represent a trustworthy summary of what booted. So what gets measured? In the simplest mental model, firmware measures bootloader, bootloader measures kernel, kernel may measure early components. On modern systems, there are multiple PCRs, and different PCR indices correspond to different measurement domains and banks. You don't need to memorize which PCR number is which for the stock. What matters is that PCRs give the TPM a trustworthy summary of what booted and how it booted. PCRs matter because they let you bind key usage to platform state. This is where sealed and unsealed that we talked about in the previous section become precise. Sealing is not just encrypt this key and stash it. Sealing is make the secret or key usable only if a policy evaluates true. That policy can include these PCR values. So you can create a key that's only usable when PCRs match an expected boot chain. If the boot path changes, the PCRs change and the policy fails. The key exists, but operations are denied. The key is sealed in that case. This is how all of that turns into something operational. This is what measured secure boot actually means in practice. You don't pin identity to a single PCR value. That would be brittle and useless. Instead, you define a policy, a description of what you consider acceptable boot states. That policy can allow multiple valid paths, updates, configuration changes, and even hardware differences. And that policy becomes the gate. So now key usage isn't controlled by a flag that says secure boot enabled. It's controlled by whatever the system's measured states, by whether the system's measured state satisfies the policy you defined. The TPM isn't asking, did secure boot run? It's answering a stronger question. Is this system in a state where identity is allowed to be exercised at all? Now, remote attestation. Just the overview, not the full story. Remote attestation is the process of taking internal TPM facts and turning them into signed evidence that a verifier can check. Practically, that evidence often takes the form of what's called a TPM quote, a signed statement that includes selected PCR values and a verifier-provided challenge, usually a nonce. Attestation evidence can also include claims about keys, where they were generated, what attributes they have, and what policy they're bound to. All of this is signed by an attestation key. The key idea for now is this. Attestation is how you export claims, not secrets. So let's talk about integration patterns without turning this into a full deployment arc. The first pattern is device enrollment. On enrollment, you mint an application identity key inside the TPM. Optionally, and optional is important here, this is where endorsement keys and attestations come in. The device may first attest that it is a genuine TPM in an acceptable state. You then take the identity public key and register it with your server, often as a certificate or public key record. And from that point forward, the device proves continuity by producing TPM-backed operations with that key. The second pattern is ongoing verification. You don't want enrollment to be a one-time ceremony and then blind trust forever. So systems periodically ask for updated evidence, fresh signatures or attestation summaries or policy confirmations, depending on your threat model. The point is not to micromanage the device. The point is to detect drift, platform state changes, key attribution changes, key attributes changes, policy expectation changes. You're continuously validating that identity is still anchored the way you intended, not just that it once was. So here's the practical synthesis for TPMs. A TPM gives you keys with explicit roles. EK for bootstrapping trust in the TPM's identity, AK for signing evidence, and application identity keys for workload identity and signing. It gives you PCRs to represent boot integrity and gives you sealing policies to bind key usability to expected state. That's why the TPM isn't just a safe, it's a safe that only opens under the right conditions. Now let's switch platforms and talk about Apple. On the surface, Apple's Secure Enclave and TPM solve a similar problem. Isolate keys from the operating system and enforce policy in hardware. When we say Secure Enclave, we mean a secure coprocessor that runs its own microkernel, has its own memory and random number generator, and operates under the assumption that the main OS could eventually be compromised. Architecturally, that's not entirely foreign to TPMs, especially integrated TPMs. The difference is in integration details and control surface. A TPM exposes a standard command interface defined by specification. The Secure Enclave is deeply integrated into Apple's silicon and operating system. You don't send raw security commands to it in the same way. Instead, you interact through Apple's system APIs, and the OS mediates access while the Enclave enforces key isolation internally. The Enclave is still a distinct trust domain. The OS cannot read its internal memory, cannot extract the keys, and cannot bypass its policy engine. The operating system is a client of the Enclave, not its owner. From an identity perspective, the most important property is the same as with TPMs. Keys that generated inside the Secure Enclave are non-exportable by design. The private key never appears in system RAM, never lands on disk in plain text, and never crosses into application memory. Applications can request operations like signing or decryption. They cannot retrieve the key material itself, and that restriction is enforced by hardware, not by convention. So Apple exposes this through familiar APIs, keychain services, and secure enclave-specific key attributes. From an app's point of view, you declare key properties, generate in Secure Enclave, mark as a non-exportable, optionally require user presence, restrict to this app. The OS brokers the request, the Enclave performs the cryptographic work, policy enforcement happens below the OS boundary. Conceptually, the Apple API is simpler than with TPMs. When you later request a signature, the OS forwards the request into the Enclave checks policy and returns only the result. If the app lacks entitlement, if the device state violates constraints, or if usage rules aren't satisfied, the Enclave denies the operation. There's no fallback path, there's no alternate API, the hardware enforces the decision. And just like with TPMs, this changes the attack surface. Even if an attacker compromised the application process or the kernel, they still cannot extract the private key. At most, they can attempt to invoke legitimate signing operations while the compromised code is running. They cannot copy the identity to another device, they cannot mint replicas, the identity remains bound to that specific hardware. So Apple's identity model also differs philosophically from TPM deployments. Keys are typically per app, not globally shared per device. When an app generates a Secure Enclave key, it is cryptographically scoped to that application's identity and the device. Another app cannot reuse it, even if running under the same user account. Isolation is enforced by the OS entitlements and hardware policy. That containment model is deliberate. Apple does not default to a single universal device identity key. Instead, each application can have its own hardware-backed identity. If one app is compromised, its identity does not automatically spill into other apps. The Enclave enforces that segmentation. Identity becomes granular rather than monolithic. Now, at a high level, Apple also provides attestation for Secure Enclave keys. When a key is created, the system can produce a signed statement asserting that the key was generated in genuine Apple hardware inside the Secure Enclave with specific attributes. That statement chains back to Apple control roots embedded at manufacturing time. The key idea is not blind vendor trust. The key idea is verifiable claims. With this flow, an application server can validate that the public key corresponds to a private key generated in hardware, marked non-exportable and bound to a specific class of device. Identity becomes something you verify cryptographically, not something you infer from a header. This integrates directly into certificate flows and device management. In enterprise environments, modern MDM mobile device management systems rely on hardware-backed key generation during enrollment. The device proves key provenance. The measurement server verifies attestation. The management server verifies attestation. A certificate is issued that is bound to that hardware-backed key. From then on, the device authenticates using identity that cannot be cloned. As I mentioned earlier, one practical pattern on Apple platform is per app client identity. An application generates a key pair inside the Secure Enclave and registers the public key with its backhand. From that point forward, sensitive requests assign with that enclave-backed private key. In iOS, when the app is deleted, its keychain items, including Secure Enclave keys, are removed. A full device erase also removes them. The private key is hardware bound and does not migrate to another device, even through backups. That means identity is tied to that installation on that device, not to a copyable secret. Another pattern is device-bound certificates. With them, the Secure Enclave key becomes the private key for a client certificate. Backend services treat that certificate as representing a specific physical device. Copying that certificate file is useless without the original hardware. The cryptographic identity remains anchored in silicon. In compliance-heavy environments, identity becomes a continuity signal. The device doesn't just authenticate once at enrollment, it continues proving possession of the same Secure Enclave protected private key by performing cryptographic operations with it. If the device is wiped, replaced, or the Enclave key is destroyed, that private key is gone. The next authentication will use a different key, identity continuity breaks, and that break is detectable. It's important to state that what the Secure Enclave does not do. It does not prevent all abuse. If malicious code runs inside the legitimate app process, it may request signatures, but it cannot extract the key. It cannot scale that identity elsewhere. That compromise remains local and bounded. This is Apple's architectural diagram of the Secure Enclave. We're not going to dive into the details. Instead, we want to recap how is Secure Enclave different from a TPM. TPMs are standardized, vendor-neutral components heavily focused on boot integrity and platform measurements. Secure Enclave is vertically integrated, tightly coupled to the Apple's OS security model and optimized for per app and per device isolation at global consumer scale. Different architectures, same core property. Identity lives in hardware, keys are non-exportable, policies enforced below the OS. Evidence can be produced about key provenance, the OS can request cryptographic operations, it cannot override the enclave's guarantees. A kernel compromise does not automatically become an identity compromise, the operating system can misbehave, and identity can still be anchored correctly. That separation is rare in software systems. Let's move to Android. Natural question is, do we get the same guarantees? The answer is sometimes. Android absolutely supports hardware-backed keys, but unlike Apple, Android is an ecosystem, not a vertically integrated stack. The guarantees depend on device class, OS version, vendor implementation, and whether Strongbox, which we'll cover a bit later, is present. So the model is powerful, but it is not uniform. At the API level, everything starts with the Android key store system. Applications generate keys using this keygen parameter spec and request that those keys be hardware backed. If hardware support exists, the key is generated inside a trusted execution environment, historically ARM trust zone, which we'll cover in the next slide, and on some devices, a discrete secure module called Strongbox. The private key material is not returned to the app. The key store provides only operations. This is the typical hardware model we've seen so far. Under the hood, most devices implement hardware-backed keys using a trusted execution environment, historically ARM trust zone. Trust zone is not a separate chip, it's a secure execution mode of the main CPU. In that model, the secure world runs isolated code and stores key material outside normal Android user space. The Linux kernel, system services, and even root level compromises in this normal world cannot directly extract those keys. But this isolation is implementation dependent and vendor specific. Strongbox is where Android gets closer to the TPM or Secure Enclave model. Strongbox is a discrete hardware security module separate from the main SoC, with its own CPU, secure storage, and random number generator. When a device advertises strongbox support, keys can be generated in that separate hardware boundary. This proves stronger resistance to side channel and OS level compromises compared to trust zone only devices. The important nuance of Android is that not all hardware-backed keys are equal. On some devices, hardware-backed means trusted execution environment-backed. On others, it means strongbox-backed. On lower end or older devices, a key request marked hardware-backed may silently fall back to software if hardware support is unavailable. If you do not check, you may believe you have a hardware anchor when you do not. Let's talk about attestation. Android supports key attestation, which produces a certificate chain rooted in Google's hardware attestation root. The attestation record includes fields describing whether the key is inside secure hardware, whether it is strongbox backed, whether rollback resistance is enforced, and what OS patch level was present when the key was generated. That evidence is what lets your application backend reason about guarantees. However, as we alluded to before, attestation capabilities vary by device and Android version. Older devices support basic attestation. Newer ones support hardware-enforced attestation with verified boot state included. Some include device properties like verified boot hash and OS version in the attestation extension. Others provide more limited data. This inconsistency is not a bug. It's the reality of the heterogeneous Android ecosystem. So practically, you cannot treat Android hardware backed as a binary property. It is a spectrum. You must inspect the attestation certificate extensions. You must parse the key description ASN.1 structure. You must verify the certificate chain against Google's published root, and you must evaluate claims against policy. Is strongbox required? Is verified boot required? Is patch level recent enough? This leads to a design strategy shift. Instead of asking, is this hardware backed? You define tiers. For example, tier 1 might require strongbox, verified boot, rollback resistance, and recent patch level. Tier 2 might allow trusted execution environment-backed keys with verified boot. Tier 3 might accept software-backed keys but restrict privileges. Your application backend should enforce policy based on attested capability, not assumptions. Capability detection must happen at runtime. When generating the key, you can request strongbox via this method. If the device lacks strongbox, key generation will fail. That failure is a signal, not an error. You catch it, adjust policy, and decide whether to degrade gracefully or block the feature. Hardware capability becomes an input into your trust model. Another point of detail, Android keys can be bound to device unlock state or user authentication. You can require a biometric confirmation per use or specify validity windows under unlock. That policy enforcement happens inside secure hardware. For high-risk operations, this means an attacker who gains code execution still cannot trigger key operations without satisfying user presence constraint. The user must be there and confirm the operation. But fragmentation remains the core challenge here. Some OEMs ship buggy attestation implementations. Some devices are rooted or bootloader unlocked. A verified boot state may be orange or yellow. Your server must treat these states explicitly. A verified boot state of green indicates the device booted an intact system image signed by the manufacturer. Anything else is signal you must interpret, not ignore. The operational takeaway is that Android can absolutely provide hardware-anchored identity. You can generate a per-app key attested, register the public key, and require all sensitive requests to be signed. But you cannot assume uniform guarantees across your fleet. You must design to handle the special cases. That means building policy evaluation into your application backend, not hard-coding assumptions into the client. It means logging attestation claims for auditing. It means having fallback tiers that do not completely disable functionality but appropriately reduce trust. And it means continuously re-evaluating device posture over time. So does Android give you the same guarantees as a TPM or Secure Enclave? Sometimes yes, sometimes almost, sometimes partially. The platform gives you the primitives, your software architecture determines whether those primitives become real security boundaries. You can build strong hardware-backed identity on Android, but unlike a single vendor stack, you have to treat hardware capability as variable input. The guarantees are real, but they're conditional. And if you design for that variability, Android becomes a powerful rather than fragile. All right, so we talked about roots of trust, secure processors, non-exportable keys, PCR, secure enclave, strongbox, but none of that matters to a remote server unless it can verify it. So let's focus on this core question. How does a backend sitting somewhere on the internet know that a key really lives inside hardware and that the device is in an acceptable state? That is what attestation solves. Attestation turns internal hardware facts into externally verifiable evidence. At its simplest, attestation is two things combined: evidence and a signature. Evidence is structured data about the device and the key. A signature binds that data to a hardware-rooted key. The device says, in effect, here are my claims. The hardware says, I cryptographically stand behind those claims. The verifier does not trust the device's software. It verifies the signature and evaluates the claims itself. Attestation is not about secrecy, it's about proof. Let's be precise what can be claimed. First, key provenance. An attestation statement can assert that a key was generated inside hardware, not imported. On TPMs, this shows up in key attributes like fixed TPM and sensitive data origin. On Android, it appears in the key description extension. On Apple platforms, attestation can assert that the secure enclave key was created on device. This answers a specific question. Was this key born inside a protected boundary? Second, non-exportability. The attestation evidence can assert that the key is marked non-exportable and bound to hardware. In TPM terms, attributes constrain duplication and migration. In Android attestation, you'll see flags indicating hardware enforcement and origin. In Apple's model, the attestation certificate binds the key to the secure enclave. There is an important nuance. This is not a runtime promise. It's a cryptographically signed claim about how the key was created and constrained. Third, platform state. On TPM systems, this often means PCR values included in a TPM quote. The attestation key signs selecting PCRs plus a nonce supplied by the verifier that proves both platform state and freshness. On Android, attestation includes verified boot state, bootloader lock status, OS version, and patch level. On Apple, device attestation can include assertions about device class and software state. Attestation lets the verifier reason about what booted, not just who signed. Verification has two distinct phases. The first is cryptographic verification. You validate the signature of the attestation statement. You validate the certificate chain. You confirm that the attestation key chains up to a known root, a TPM manufacturer root, Google's attestation root, or Apple's attestation root. If that chain is invalid, everything stops. No policy logic matters if cryptography fails. This phase answers, did the hardware really sign this? The second phase is policy evaluation. This is where engineering discipline is important. You do not blindly accept any valid attestation. You parse the claims and evaluate them against your own requirements. Is the bootloader locked? Is verified boot state green? Is the OS patch level recent enough? Was the key generated in a strongbox or only in a trusted execution environment? Do PCR values match a known good baseline? Attestation verification is not binary, it is structured policy evaluation. A common misconception is that attestation equals vendor trust. That's not accurate. You're not trusting a marketing statement, you're verifying a signature against a root certificate you choose to trust. That trust anchor is explicit, but the claims are machine readable. The evaluation logic is yours. You can pin acceptable firmware versions. You can require strongbox-backed keys. You can reject unlocked bootloaders. You can log every attestation claim for audit. Attestation is cryptographic evidence, not a press release. There's also subtle but critical detail, freshness. Attestation statements must include a nonce provided by the verifier. Without that, an attacker could replay an old attestation captured from a healthy device. In TPM terminology, the nonce is included in the quote structure and signed by the attestation key. In Android attestation, the challenge is embedded in the certificate extension and signed. The server generates the nonce, the hardware signs it, and the server verifies it. Freshness prevents replay attacks. Evidence must be current. And one more important boundary. Attestation proves properties of hardware and boot state. It does not prove absence of compromise at higher layers. If malicious code runs inside a legitimate process, attestation might still succeed. That is not a flaw. It defines the scope. Attestation proves that keys are hardware generated, non-exportable, and bound to certain platform conditions. It does not prove that your application code is bug-free or that no runtime exploit exists. Hence, you must align policy with realistic threat models. Operationally, attestation becomes part of enrollment and ongoing validation. During enrollment, you verify that the device-generated key meets your hardware and state requirements before you register it. During ongoing sessions, you may periodically re-attest to detect drift. Bootloader unlocked, OS downgraded, firmware changed. You should not treat attestation as a one-time ceremony. You treat it as evidence that can be re-evaluated. That's the shift from static identity to measured identity. And this is where everything we discussed earlier converges. A key by itself is just a cryptographic primitive. Hardware boundary by itself is just a containment mechanism. Attestation measurements themselves are just hashes. Attestation connects them. It turns internal hardware facts into signed, verifiable evidence that a remote system can evaluate. Now identity is no longer who has the thing. It is no longer who has the certificate. It is what physical device in what measured state produced this proof. That's the transition. Now identity is bound to physics, not paperwork. At this point, the question shifts from is it secure to how do we actually ship this? Hardware-backed identity is not a feature you toggle, it's a life cycle you design. Enrollment, rotation, revocation, recovery, these are not afterthoughts. If you get the life cycle wrong, the hardware guarantees don't save you. So let's walk through what a production-grade flow actually looks like. Enrollment starts on the device. The first step is key generation inside hardware. Generated in place, that key becomes the long-term device anchor. It might be an ECC P256 signing key, it might be RSA. The algorithm is not important since our current focus is on the overall policy, on the overall process. The important part is origin, created under hardware policy, bound to that specific root of trust. Immediately after generation comes attestation, which is optional. The device produces evidence, meaning a signature, that this key was hardware generated and constrained as expected. Your backend verifies the signature chain, validates attributes, checks state claims, and evaluates policy. Only if those checks pass do you accept this key as representing a device. Enrollment is conditional. You're not just registering a key, you're registering verified hardware provenance. So when our agent enrolls, it's not just saying, here's my public key. It is saying, here's proof that this key was born inside hardware on this device. Once verified, the backend binds that public key to a device identity. All future credentials are issued only after proof of possession of that hardware-backed key. Credentials like OAuth tokens, mTLS certificates, session keys, the hardware key becomes the root. Everything else is derived from it. Hardware makes identity durable. Certificates and tokens make it operational. Now, rotation. You don't rotate the hardware key routinely. That key anchors device continuity. What you rotate are the credentials bound to it. You rotate certificates, not hardware identity. Rotation also supports cryptographic agility. If your backend moves from RSA to ECC or from one signature scheme to another, you can enroll a new hardware-backed key alongside the old one. Dual publish, gradually phase out. The lifecycle design allows change without mass device reprovisioning. That separation hardware anchor versus renewable credential is what keeps operations manageable at scale. Revocation is where this architecture really changes incident response. In traditional systems, compromise often means resetting a password or revoking a shared token. Here, you revoke a device identity. For our agent, that means that the specific laptop stops authenticating. Not the user, not every machine, just that hardware identity. You invalidate the certificate, you add the hardware key fingerprint to a deny list. The user account survives, but the device identity does not. You've narrowed the blast radius from person to machine. Device compromise workflows become explicit. If attestation claims change, bootloader unlocked, hardware downgraded, you can flag the device as degraded trust. Maybe you reduce privileges, maybe you require re-enrollment, maybe you quarantine access entirely. The key point is that you are acting on device posture, not guessing based on user behavior. Recovery paths must also be intentional. What happens if a motherboard is replaced? What happens if a phone is factory reset? I've heard our customers complain that the endorsement key can change on their TPM and they don't like it. But the fact is that hardware identity continuity breaks by design. Your system must treat that break as a new enrollment event, not a silent key rollover. Continuity is signal. A sudden change is either maintenance or compromise. Your application backend must have that signal. The practical takeaway is this: hardware gives you permanence. Certificates gives you flexibility. That separation is what makes this deployable at scale. Revocation and rotation become clean, scoped operations. That is how you turn hardware-backed identity from an academic property into a production system. Let's circle back to where we started. Earlier in this talk, mTLS and signatures felt insufficient. They proved possession of a key, but not where that key lived. Now the equation changes. Once the private key is hardware-backed and attested, mTLS stops being a weak assumption and becomes a strong transport carrier. The protocol itself didn't change. The root beneath it did. mTLS becomes meaningful when the certificate's private key is non-exportable and device-bound. Now, when our agent connects over mTLS, the handshake is no longer just math, it's proof that this specific device is present and active. With hardware-backed certificates, the TLS handshake now carries a device identity anchored in silicon. The client presents a certificate whose key never left secure hardware. The server validates the chain, verifies proof of possession, and ties that connection to a specific device key fingerprint. The handshake is no longer just cryptographic correctness, it becomes hardware continuity. The transport layer becomes an enforcement point rather than a convenience. But architecture still matters. In many systems, mTLS terminates at a load balancer or edge proxy. If termination happens there, you must preserve verifiable identity downstream. That can mean reestablishing mTLS to the application tier, forwarding a cryptographically protected identity header, or embedding device identity into a signed token created by the trusted edge. That full chain must remain verifiable. Now let's talk about this application layer carrier. HTTP message signatures, which is a standard widely being adopted, operate above transport. Instead of binding identity to the TLS session, they bind identity to the HTTP message itself. Method, path, headers, body digest. The signature survives proxies, survives termination, survives routing layers. Verification happens at the application backend, where business logic runs. When the signing key is hardware-backed, message signature becomes end-to-end proof, not just integrity checks. Above is a basic sequence diagram of the HTTP message signature flow. The distinction between mTLS is subtle but important. mTLS proves possession during connection establishment. HTTP message signature proves possessions per request. mTLS is connection scope. Message signatures are message scope. In environments with persistent connections, multiplexing, or complex proxy chain, application layer signatures give you tighter control over what exactly was signed and what exactly was authorized. They may also complement mTLS rather than fully replacing it. Operationally, both approaches benefit from the same root. Hardware generates the key, attestation proves its properties, a certificate binds that key to backend identity. Then protocol carries that identity forward. Whether you enforce per session or per request, the verification logic is consistent. Validate signature, validate certificate chain, validate policy claims. The transport is interchangeable because the trust anchor remains constant. There are some real challenges here. Library support for HTTP message signatures is improving, but uneven across languages. Some platforms provide first-class hardware key access for TLS, but not for arbitrary message signing. On Android, you must ensure the key store key supports the required signature algorithm. On Apple platforms, Secure Enclave keys may also require you to use certain algorithms. Overall, protocol flexibility is somewhat limited by hardware capabilities and API surfaces. Operational complexity is also non-trivial. Certificate issuance, renewal, and revocation must integrate with device lifecycle. Edge proxies must be configured to preserve or reestablish trust correctly. Logging must include device key identifiers, not just user IDs. Failure modes must be explicit. Expired certificate, attestation policy failure, downgraded device posture. The protocol layer exposes errors that were previously invisible when identity was just a bearer token. The mental model now becomes linear and composable. Let me reiterate. Hardware creates a non-exportable key. Attestation produces verifiable claims about that key. A certificate or key registration binds it to an application backend identity. Protocol, whether mTLS or HTTP signatures or something else, carries proof of possession in real traffic. Each layer does one job. None of them alone is sufficient. Together, they create continuity from silicon to request. That layered model is what turns cryptography into architecture. Let's step back and ask the practical question. What actually changes? What attacks stop working the way they used to? The first category is stolen credentials. If identity is just a token, theft scales instantly. One leaked secret becomes infinite clients. But if identity is bound to hardware, stealing a token is no longer enough. The attacker must also control the device that holds the non-exportable key. Theft stops scaling. It becomes local. An attacker can compromise one laptop. They cannot turn that into 1,000 authenticated agents. Second, clone workloads. In software-only systems, copying a container image, a VM snapshot, or a file system often means copying identity along with it. If the key is exportable, the clone is indistinguishable from the original. With hardware-backed keys, cloning stops at the boundary. You can duplicate code, you can duplicate configuration, you cannot duplicate the private key sealed inside a secure processor. Third, replay. Earlier we talked about bearer tokens and signed blobs being replayed from somewhere else. Attestation with freshness changes that dynamic. Nonces, timestamps, and proof of possession make evidence bounded in time. A captured attestation or signed request cannot simply be replayed later from another machine. Evidence must be current. Identity must actively prove itself. A replay becomes detectable instead of invisible. Fourth, shadow clients. In many systems today, you cannot reliably tell where the traffic is coming from your original application or from a reverse engineered script. If the only requirement is present the right bytes, shadow clients flourish. But if every request must be signed by a device-bound hardware-generated key that was attested at enrollment, shadow clients become obvious. They lack the anchor. They fail policy. Notice what did not change. Cryptography did not get stronger. Algorithms did not get magical. Attackers did not get less capable. What changed is leverage. They can still compromise software. They can still inject code, but they cannot take one compromised identity and multiply it across infrastructure. The blast radius narrows from ecosystem-wide to device-bound. Attackers don't lose skill, they lose leverage. This also changes how you think about incident response. You no longer reset a shared secret, you revoke a device identity. You invalidate the certificate tied to a hardware key. You mark a key fingerprint as degraded. Identity becomes scoped and revocable at the machine level. Containment becomes precise instead of global. And that leads to a deeper shift in thinking. For years, we've asked the same question. Is this credential valid? Does this token parse? Does this signature verify? Does this certificate chain correctly? Those are syntactic checks. They answer whether the math works. They do not answer whether the entity behind the math is what you think it is. And the new question is different. Not, is this credential valid, but what physical thing could have produced this proof? What device, in what measured state, inside what hardware boundary generated this signature? That reframing is the heart of hardware-backed authentication. Identity stops being a string that passes validation. It becomes evidence tied to a specific piece of silicon. Protocols still matter, standards still matter, interoperability still matters. But protocols do not create trust, they carry it. Trust originates somewhere deeper. It originates in roots of trust, in non-exportable keys, in measured state, in attested evidence. When those pieces align, identity is no longer a guess. It is a property grounded in hardware. So if you lead with one mental model, let it be this. Hardware gives identity weight. Attestation turns that weight into evidence. Protocol carries that evidence across the network. And policy decides what you accept. When those layers are designed intentionally, impersonation becomes harder to scale, easier to detect, and cleaner to contain. Protocols don't create trust. Physics does. Before I wrap up, I want to pause on this. These are some of the teams using Fleet in production today. They're very different organizations with very different constraints. We've learned a lot from working with customers like these. Many of the lessons I talked about come from operating at this kind of scale under real conditions. That's it for this talk. This talk aligns with how you think about hardware-backed security. I'd love to hear how you're approaching it in your own systems. And there's a few links to Fleet, and we are hiring, and here's some links where you can find me and some of my work. Thanks for listening. I run a little bit long.